are back today, and we're going to talk about our kind of first distribution that we are going to be working with. We talked about the three last time that we're going to work with primarily in this course, which is Gaussian or normal probability distribution, the student t-distribution, the chi-squared distribution. That comes up a little bit later on in this course, lecture 4. But today we are going to deal with our kind of the first distribution, kind of your normal or Gaussian distribution, and specifically the probability density function, or PDF. Now, this is distinct from the PDF for our Engineering 45 Material Science course, but that's a discussion for another day and definitely another video. So again, usually we do not know, we work with samples because we do not know the population, but let's just, it's because really it's impractical or impossible to work with the entire population. But let's say, for example, that we have an infinite population of data, and we actually kind of know this, we know the information about our population. If we assume we can figure out and essentially describe the probability of obtaining some measurand x based on kind of this distribution. So if I'm trying to figure out, okay, what's the probability that my measurement falls between this range and this range, I could use this PDF function, integrate this area, and figure out what is that probability. So one of the key things of the PDF is that the probability of measuring like some value x is not just this point here. Again, we need to kind of, the probability density function, it allows you that between two values, x of 1, x of 2, we'll measure the probability of measuring some measurand within this range. We have to integrate it, and then we could kind of figure out, okay, what's that probability that we could find a measurand between these values. So that's kind of the key concept behind your probability density function or PDF. So let's take a quick look at that right now. So before we get into that, when you look at kind of normal distributions and probability density function, you are looking, again, kind of the probability and to measure some measurand. So the PDF, or like kind of this Gaussian or normal distribution, you can kind of see that it's hard to kind of observe in this graph, but as your standard deviation increases, your graph widens. So it becomes more, larger standard deviation means kind of there's more uncertainty essentially in your measurement. There's a larger distribution. So again, the probability of measuring basically at 0 decreases, and this graph gets wider and wider. And you could even extend this to kind of, let me change colors. Large standard deviation. So let's say that this is much, much, much greater than any of the ones in here. You could kind of see a distribution that goes something probably like this. Really exaggerated, obviously, but again, that's kind of the concept between your probability density function. The probability of measuring, if the Gaussian is tight, if your standard deviation is really, 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 really small, your curve is going to be really, really tight and centered around essentially one value. So it's highly probable that you'll measure here, low probability here. As your standard deviation increases, there's a higher probability of measuring measurands in that area. So that's effectively what your probability density function does. So we'll actually skip here a little bit and go to, this is essentially the function that you're working with for your Gaussian probability density function. So again, it's a function of several variables. Mu, which is the mean of the entire population. This is your population. I'm stuck on that now. This is your population mean. Very, very important. Not your sample mean, the mean of the entire population. And sigma is the standard deviation, STD, of the entire population. So these are key kind of parameters here, the entire population. So we are assuming, again, when we're working here in the Gaussian, the probability density function, we are assuming that we know the mean and standard deviation of the entire population. This is not often the case, but we're going to see that we can invoke, again, that central limit theorem to kind of get around this practical, that we are never really working with the mean and the standard deviation. We don't know information about the entire population. So oftentimes we can approximate, again, as long as we have a large number of measurements and greater than or equal to 30, we can approximate the mean as x bar, which is essentially this is the mean of a sample, as long as we have a large sample size. And we're assuming that the population is PDF or normally distributed. That's the key assumption. We're assuming that population distribution, like we talked about last time, is Gaussian. Oftentimes, it may not be. It may be some weird kind of function, but that's going to be the assumption that we make in order to kind of perform this analysis. So you have to assume that, or it has to be stated explicitly in the problem. So, excellent. But we're going to, again, we're going to talk about the central limit theorem as well. And these are just definitions of standard deviation, how to calculate it. You should hopefully know that at this point. Or, again, just type in Mathematica, standard deviation, mean, et cetera, et cetera, et cetera. So let's go back. Now that we know this function. So we talked about previously that the probability density function is just, what it's plotting is essentially the probability of measuring some measurand between, certain values, x of 1 and x of 2. So that's kind of what you kind of drew that previously, in the last kind of slide here. Let me go back. We kind of drew that out here. We had a little bit of brief discussion, but let's do a quick little problem in question. So this is the probability of just measuring some measurand between, again, x of 1, x sub 2 in our distribution. So if I have this is x of 1, this is x of 2. Now, what's the probability of measuring some measurand between minus infinity to infinity? Take a quick second, don't look at the notes. Well, the probability of me measuring any measurand between with values between minus infinity to infinity, it better be 1. I better have 100% probability. If I break that law, mathematicians are gonna attack you and go insane. But anyways, so this is kind of a key aspect. So the probability is unity. So from minus infinity to infinity, the probability of measuring some measurand is just 1, 100%. You'll definitely measure some value between, I promise you. In this course, if you are measuring some value between, you will always measure some value between minus infinity and infinity. We will not break essentially those laws. So that's kind of, again, one of the nice and unique things about that working with that probability density function. Excellent. Outliers. So oftentimes when you're doing research, you'll hear people argue kind of when we could take a data point, when is a data point an outlier, when is it a legitimate data point, et cetera, and you'll especially run into this, again, if you work with people with different backgrounds and different disciplines, and unfortunately unscrupulous either researchers or unscrupulous industry people as well. So you really need to be, as ethical engineers, you really want to obviously always show all of your data points, even if you have, if we have a plot here of, y versus x, and everything's looking nice and kind of linear, but then you have one point that is just way over here, you still want to show that data point on your graph. But there are tools and there's some methodology that we're going to use in this class to identify essentially an outlier point. So in this class, we are going to disregard a data point as illegitimate if the data point exceeds 3 sigma. So if a data point, some measurand x sub 1 is greater than, or if x1 is also like less than, if it's plus or minus, basically x1 is plus or minus 3 sigma from your population mean or your x bar, we could say we could disregard that data point. Why can we disregard that data point? Well, it goes back to looking at this curve here. If we're 3 sigma away, we're in kind of the super low probability of making that measurement. So we can assume that's going to be our quantitative metric on how we decide a data point is an outlier. But again, you must show this data point. But you could just on your graph kind of show an x, say that this is greater than 3 sigma from the other measurements, and you'll be fine. So that's kind of what I want you, or what I hope you will do moving forward in terms of how we deal and play, or basically how we work with outliers. Now we can simplify our Gaussian and rewrite our expression to be a little bit more simple if we just basically derive or write the following expression. So if we could rewrite our expression here and introduce some arbitrary variable z. So once we introduce z, we substitute it in our expression. Now we have this equation right here. So f sub z. Why do we have z? Because we are going to be using essentially z tables, and it's going to allow us to kind of do some really nice, simple, easy calculations. And we're going to work on that a little bit later on in this, actually in this video. So one of the things that we've been talking, so we'll get to that a little bit later, but it's just some arbitrary variable z. Again, we still have all of our different kind of parameters written there. So no worries on that end. So now we've been talking a lot and mentioning briefly these idea of confidence intervals. So and we said typically we're working with confidence intervals of 95%, it could be 90, it could be 99, it could be 50, 60, et cetera, et cetera, et cetera. One of the ways that you can kind of think about confidence intervals is that basically if I make a measurement, I'm 95% confident that it's going to fall between bounds of x of 1 and x of 2, just like we saw in our probability distribution. So if I'm 95% confident that my measurement's going to fall between here and here, what I'm basically saying is that 95% of the data should fall basically in between those bounds. So I need to figure out what are the bounds where 95% of my data are going to fall. So how am I going to calculate that? Well, all I'm going to do, if I know, again, I'm going to need to know some information. So I need to kind of figure out basically what is x, and I'm going to need to integrate. We're going to see that in a second. I'm going to need, so here's my probability distribution, probability density function, my PDF here. Here's my z value, just substituting it back in for my z here. See if I put sigma equal to 1, and not sigma, if I put this guy equal to 1, I reproduce this, I could kind of get these different values, et cetera, et cetera. But if I want to find where 95% of my data falls, and I'm just arbitrarily setting sigma equal to 1, all I have to do is integrate my PDF, and I need to solve for x, because I'm basically solving for x as a function of x times sigma. So what I'm going to get is basically these values in terms of multiples of my standard deviation. Again, if I know my standard deviation, I could just get the exact value, and we'll see that in a second, but I'm keeping this very general at this point. So all I have to do is integrate this, my z function, and then solve at these bounds. So I'm having it symmetrically, I'm kind of figuring out what are the symmetric bounds. Again, there's lots of different bounds where I could find 95% of my data, but again, I'm assuming that we're kind of setting it at that mean. And then all I'm doing is just figuring out, okay, when does this integral times 100 to get it in percentages, when does it equal 90%? When does it equal 95%? When does it equal 99%? And I'm just solving for x. That's all what's happening here. So that's all that I'm doing. So what I end up with, going back here, so for my 95% confidence interval, I know that my measure and here, so for 90%, for example, let me get my pen back. So for 90%, I know that my measure and needs to be basically my measure and x of 1 or x of 2, whichever it has to be mu plus or minus 1.64 sigma. For 95%, it should be mu plus or minus 1.96 sigma. So I need to be basic, and it could be mu, or it could be, you could approximate it as x bar. But I need to make sure 95% of my data is going to fall between mu plus or minus 1.6 sigma. Mu plus or minus 1.96 sigma for 95%. And you can see for 99%, 2.578, plus or minus that for sigma. You can calculate any arbitrary confidence interval mathematically just using it's just integrating. So you can solve problems like this. Luckily, and again, this is your preference. So if you like to do the integration, if you could do the integration by hand, good, more power to you. I'm going to use Mathematica, but if you don't like either of those methods, and this could be a little bit cumbersome, especially for exams, one of the nice things is because these are kind of so commonly used, we actually have what's called these Z tables. So they're basically tables that it shows the integration from values from 0, so centered at the mean, or actually values of z. Z we know is x minus mu over sigma. We had that defined previously. So if my z is equal to 0, What does that mean? It means my measurand, x, is equal to mu. So when I'm centered, when I'm looking just at when I'm at that, basically my mean, when I'm centered at my normal distribution, my z-value is 0. So this table will give you values, the integral, it basically gives you the integration, the area under this curve, from values from 0 to different z-values. So if I want to look at a z-value of equal to 0.23, I'm going to go from here, here, and then 0.23 is right here. And that's how you kind of read and utilize essentially these z-tables. So that's one way to kind of run through and do these problems in a little bit more efficient and quick manner, especially for your exams. But you can always use Mathematica too, whichever you are more comfortable with. So let's go ahead with that knowledge. Let's do some values. So what's the area under our standard normal distribution, our PDF, between the values of z and between values of minus 1.43 and 1 plus 1.43 z? Well, let's look at it. Let's go ahead and go back here. So let's look at my z table. So I'm looking for z values of z plus or minus 1.43. So 1.4, 0, 1, 2, 3, I believe. So it should be about z of 1.43, the area, z equals 1.43, is equal to 0.4236 approximately. What do I do? I mean, how am I going to find out? There's no negative values here. How do I find negative values of z? Remember, this curve is symmetric. So for the area of z equals minus 1.43, it's just going to be the exact same. So the total area under this curve is just going to be between plus or minus 1.43 z is just going to be 4236 times 2. That's it. Let's confirm that in Mathematica, as always. Our double check. Yeah, that's it. So when we're asked on the next question, what percent of the population lies within this range, you just multiply this by 100 to convert to percentage. So 84.72% is going to be within this range. That's it. That's all you're working with here. Now, the last part of that problem asks, let's go up here, what range of z will contain 90% of the data? So I love to ask inverse problems. So if I'm trying to figure out what z values, what plus or minus z values, so I'm looking for z plus or minus z, what are those values that give me 90% of my data? Well, I know this curve is symmetric, right? So if I want 90% of my data, 90 divided by 2 is 0.45, right? Or, 0.9 divided by 2. Hopefully I could use this without 0.45. So if I'm looking at my table, 0.45, it's going to be basically between here. So you could take the average. I could do 1.6, 1.65. Really, it's not too bad. But you could take the difference, 1.645, and then you could get that for 90%. And actually, you can kind of confirm that with what we did previously, 1.64485. So again, you could solve for that exactly. But yeah, so that's how you use the z-tables in a nutshell. So let's do one more example. It's a little more fun. So I'm measuring, and we'll do these examples next time. I'm measuring the swimming velocity of bacterial E. coli. So they do these kind of cool, basically run and tumble mechanisms. So if there's food here, they'll perform chemotaxis, and so your bacteria will kind of like stumble around, then they kind of like seek out food, and they kind of like twirl and randomly go again, and then they seek out food, and then they kind of do this like, and then finally they get to the food source and they just stick there forever, and then they create basically these biofilms. But anyway, so measured the velocity, bacterial E. coli 135 times. Mean velocity of the population was determined to be this. Standard deviation was determined to be this. I'm interested in the velocity measurements between this value and this value, and the percentage of the population that will fall within this range. I'm planning to claim in my Nature paper, very ambitious, that 95% of the data is going to fall within this range. So first thing, let's kind of break down this problem. So I measured the velocity 135 times. So n greater than or equal to 30, large data samples, we could kind of make some of these assumptions that x bar is approximately mu. And anyways, we can kind of work with this data set. We could use our kind of traditional methods. We also need to make an additional assumption that our population our population distribution is normally distributed. So we also know in this problem statement that mu is equal to 3 micrometers per second. Standard deviation is equal to 0.1 micrometers per second. And then we're interested in our x sub 1, which is 2.857, and our x sub 2, which is equal to 0.3 micrometers per second. And we need to figure out what is the percentage of the population that falls between these two measurands, x sub 1 and x sub 2. So let's calculate z. Well, you have our x's, you have mu's, so we're plugging and chugging. So I have my function z here. So for 2.857, it's minus 1.43. For z, 3.14, it is 1.43. So we recover again that like the same essentially value. So we look up 1.43 in our table, just like we did previously. We'll find it's 0.4236, which we're symmetric. So you just multiply by 2 and 100, and you're good to go. That's it. So we've calculated z. We've calculated the area in the standard distribution. We figured out the percent of my data that's going to fall within that range. Now the question is, how many measurements fall within that range? So we have the percentage. Now, if we want to know the number of measurements, you just multiply by the total number of measurements. So 114 should fall within that range. And finally, what range of velocities will contain 95% of my data? Well, I know that's going to be between plus or minus 1.96 sigma. So mu plus or minus 1.96 sigma. So I could just calculate that out, and I could explicitly, solve for those values. So I could say that I know that that is going to occur when z equals 1.96. So if z equals 1.96, x minus mu over sigma, I know this, I'm solving for this, plus or minus. So you just rearrange that equation and solve for x. That's it. So that was pretty quick, but you have the Mathematica notebook. Hopefully you go back through this and reproduce this, and then next time we're going to do even more examples. And on the problem set, we'll have even more examples. And on the exam, there's going to be even more examples. So on the practice exam, there's going to be even more examples. So no worries, you're going to be sick of doing this at this point. It'll be second nature. All right, I'll see you in the next video. Thanks. Bye.